Good morning or good afternoon or good evening to everybody, and thank you very much for joining today's webinar. My name is Richard Smith and I'm Global Applications Manager at Taylor Hobson. In this webinar, we will take a look at some of the examples of the measurement and analysis of diameter using Taylor Hobson's PGI NOVUS and Metrology 4.0 software. We will also see how calibrations and alignments are essential for achieving accurate results. So let's start by looking at some applications using the PGI NOVUS and Metrology 4.0. There are many types of application for diameter measurement, and there's just three examples shown here. Ball screw axial measurement, looking at the pitch circle diameter, bearings and gears. We're going to take a look at the measurement of a roller bearing, where we're also interested in various dimensions and diameters. My colleagues put the bearing in place, started the measurement, and we've made contact with the surface. We're measuring the upper external surface at the moment. We're automatically detecting the beginning of the measurement and the end of the measurement. The stylus tips there are 2 micron conosphere diamond tips. So once the first measurement has been completed, we're now measuring inside on the lower internal surface. So this is the second of the 4 measurements that we're going to take. Now the gauge moves into reverse bias mode automatically, and we measure the upper internal surface. And now finally we'll measure the lower external surface. Note that we're moving the column down each time to move to the bearing. So the gauge is in its 0 position for pretty well close to 0 for each of its measurements. And here are the results. We can see the various diameters, the internal diameter, the external diameters, and actually the wall thickness is shown here as well. We've also shown roughness and waviness alongside it. Moving on now to another example of pitch circle diameter measurement on a ball screw. But before we can measure the pitch circle diameter accurately, we have to make sure that we've aligned the ball screw to the traverse unit, to the direction of the measurement. And you can see in the picture here, if we measure accurately across the top of the part, we will get good results. If we measure with the part slightly tilted or slightly angled, we will get incorrect results, particularly on these Gothic arch shapes as well. And the smaller the shape, the more critical that is. The smaller the ball screw, the more critical that is. There's 2 examples here. One shows where we're aligning on the plane shaft area. This is example 1. And in example 2, where there is no plane shaft area, we're measuring on the crest of the thread and finding those crest positions and rotating the part such that it is aligned as shown here. So one of the things that's really needed before we can measure diameter accurately is that we need a highly stable, low noise instrument, such as Taylor Hobson's PGI NOVUS system. And this allows us to establish the precise relationship between opposing thread profiles. You can see that on the right there. To achieve all of this, we need appropriate calibration routines so that we really know the relationship between the lower stylus tip and the upper stylus tip, and we'll have a look at that in a few minutes. So in the video we're about to see, we'll see the alignment taking place. We'll see measurements of both sides of the ball screw, and then we'll see the analysis and all the results. So in this example, the first thing we're doing is auto-aligning the thread. And we're taking a measurement on this top thread here and here as well. And in each case we're cresting to find the crest position. Once the crest positions are known, the ball screw will rotate. It's sitting there on a rotary stage, and it will rotate in line with the traverse movement. We've now taken the first trace across the top. You can see that we've identified from the drawing the points to which to move. The stylus is moving using something called smart move to those points very precisely, and we're taking the lower measurement now. So once that's finished, we now combine these measurements. We know the relationship between those two traces, and we're going to combine that data together. And here it is. So what we can see here is a very clear diagram of all of the results. And in particular, you can see that we've fitted the balls of known size to the Gothic arch shapes. We know the center positions of these balls, and we've done the same thing underneath here. And we're looking at the distance, the pitch circle diameter, the PCD, between these centers, as well as looking at other dimensions such as pitch and other characteristics such as roughness, primary profile, and Gothic arch dimensions. So we've looked at surface finish here, form, Gothic arch, pitch circle diameter, and we've toleranced the results as well if we want to. One of the things that's very important on the measurement of a Gothic arch thread is that the stylus tip radius is known very exactly, and that the stylus tip radius is very good. And we've got two examples here. In the upper example, you can see that we fitted a ball to the Gothic arch thread, and that's okay. But in the second example here underneath, we've not, because of the way we've measured with the wrong stylus or the stylus of a wrong radius or bad form, we've actually got a result that hasn't got or doesn't represent the real form of the part being measured. And so that means that the fit of the ball, the bearings in each of these cases in the software, is not being fitted at the right position. And so when we look at the PCD, the pitch circle diameter, we will get a wrong value. And so this is showing the upper side, the same thing would happen on the lower side, and of course we would get a completely different reading of pitch circle diameter. So the stylus tip radius and form are critical to such measurements. Here's another example of looking at pitch circle diameter, but this time we're measuring inside this hole here on a very small hole there of diameter, in this case 3.2 millimeters. The hole is threaded And again, we're interested in the thread itself and in the diameter of the thread as before. But because the hole is so small, we have to make sure that we are measuring truly along the axis of the part. And in this case, we've used the system's capability to define these edges on this mold. This is a mold. And so we've been able to align this edge up square to the movement, to the measurement direction. And we've identified a 0 position, the origin on this part. So we're able to move directly from here into the hole very, very precisely, and also knowing that we're going to be measuring truly along the axis of the bore. For this, we've used a small bore stylus. So how do we know that those results are good? One way is to measure a ball of known radius, and that's what we've done here. The radius of this ball is known to be 0.4998 millimeters. And it's a calibrated reference ball. And what we've done here is we've done 5 sets of measurements in what we call normal mode, that's measuring downwards, and in reverse bias mode, that's measuring in the upwards direction. And we've looked at the PT in each case, the form error on the ball. We've looked at the optimized radius, the least squares arc radius, both when we're measuring in normal bias and in reverse bias. And then we've looked at the deviation of the radius from the nominal radius. And also we've repeated the whole exercise with a different stylus. This is a 45-degree included angle stylus. What I've mentioned to start with is a 60-degree included angle stylus. And finally, what we can see is that the standard deviation of the results is 20 nanometers in both cases for both styli, and the spread of results is 50 nanometers for the 60-degree stylus and 60 nanometers for the 45-degree stylus. And in each case, the radius error is very, very small indeed. The maximum we have here is 80 nanometers, and the maximum again here we have is 80 nanometers. So we can have confidence in the results we're looking at. This is an example of diameter and roughness measurement using a long stylus. This stylus is 200 millimeters long, and again it's got a diamond tip on the end. It's got a 2-micron diamond in accordance with ISO 3274, which is the recommendation for roughness. But we're able also to measure diameter here as well. So this is just another example of diameter measurement. But the thing here is that because this stylus is longer, it will of course be heavier. But the PGI NOVUS that's being used here to do these measurements is able to control the stylus force and to keep that stylus force to the correct stylus force in accordance with the ISO recommendation excuse me, for roughness measurement. On the base here, we can see that the dynamic response of such a stylus is excellent. If we repeat the measurements, this 3-line standard will show measurements overlaid on top of each other excellently without any deviations, and that's due very much to the ability of this system to control the stylus force of long styli. Let's have a look now at alignments and methods of measurement of diameter. One of the things that's critical for the measurements is making sure that, for example, on this ring gauge here, to make sure that we measure right at the crest here, and that when we measure in the reverse bias mode, that we also are on the crest. And in this case, in this diagram, we're fine. We've measured exactly on the crest. The smaller the ring gauge, the more critical it is to measure on the crest. Or the smaller the part, I should say, not just ring gauges. In this case, we've deliberately shown an error in the Y direction. This is in the Y direction, so we're looking into the traverse unit. And we've deliberately shown an error here in the Y direction, and this is the tip offset in Y. And if we measure correctly at the base here, if we crest and find this point, and then we measure at the top just by moving straight to the top, we will be some way out from the crest, and that of course will cause a diameter measurement error. So we're dealing here with tip offset, and we've just looked at tip offset in the Y direction. There is also a tip offset in the X direction, but we'll come to that a little bit later. So how do we solve this problem of the tip offset? There are two approaches. One is to, after we've crested at the bottom here, when we move to the top, we can of course crest again, but that could take some time. Now the PGI NOVUS gets round that because we know through the calibration routines the tip offset in the Y direction, and so what the system does is it won't move the it won't crest again, but it will actually just move directly. It will move this stage, this Y movement stage, directly to the crest position because it knows the tip offset between the top and the bottom tip. And the advantage of that is it can save a lot of time. Here's something else that's very, very important. And the PGI NOVUS again has built-in software to detect this error and also to allow the system to be set up very, very precisely. And this is the movement. This is looking right into the gauge here. This is a ball that we're measuring, for example, or it could be a cylinder, but it's a ball in this case. And we're looking into the gauge. So there's the lower stylus tip, there's the upper stylus tip. And you can see that the whole gauge is tilted slightly anti-clockwise, counterclockwise. And clearly what that will do is that it won't describe the right path on the part. On the right-hand side, we've resolved this by aligning the gauge using the special calibration routine. And now we're certain that we're measuring right over the crest and all the way correctly around this ball. And that really is critical. And again, the smaller the part we're measuring for, the more critical that is. And that will seriously affect the reliability and the accuracy of diameter measurements. So let's look again at diameter measurement on the PGI NOVUS. We're going to look at two different methods. The first is what we call in-gauge range measurement, and the second is using a column move. So what's the difference between these two? Let's look first of all at diameter measurement with a column move. And what we've done here is on this large bearing, we've measured near the center of the gauge range. We've taken a balanced trace at the bottom here, and the gauge range, the gauge is in its near zero position. We've now moved up, and what we've done is moved the gauge into reverse bias mode. So we're dealing with this tip here, and then we move into contact with the bearing again. And again, we're near the center of the gauge range. But notice that the column has moved on the right here through some considerable distance on this large bearing. We can also do diameter measurement in the gauge range. And in this case, we're measuring internally, and we've taking a side view, we've got a cut looking internally at what we're measuring. and it's a cut part, and we're measuring the first diameter, the second diameter, and the third diameter. We then, without moving the column, move the gauge into reverse bias mode to measure the 3 diameters again. In both cases, whether we're measuring large bearings or small bearings, the PGI Novus will give us excellent results, accurate results for diameter measurement. One of the things that's necessary when we're using the column moves that we saw in the previous example is that the quality and alignments of all of the axes are very precise, and that the material and stability of that column is very, very critical if we're going to claim to be measuring diameter accurately. We can also measure angles as well using the column move in the same way. And in this case, we've measured this injector needle, and we've measured a balance trace about 0, and we've measured over onto the cone itself. We're now measuring the same thing underneath, and again we've moved the column in each case. And the typical results here, we might see for cone measurement. Often injector cones will have several different diameters and several different angles on them, and you can see these here along with the surface finish. The example on the right is actually measuring a spherical bearing where we've taken 2 traces, and again we've been able to look at the diameter between them. Let's have a look now at diameter calibration and checks. There are a lot of things shown on this slide here, and I'd just like to point out a few things. We can see some examples on the right here of a calibration artifact that's used, and some more examples here as well. Notice that there is one calibration radius here and one underneath. So what we're able to do on the PGI Novus is to calibrate not just in the downwards direction, but also in reverse bias in the upwards direction. So we have 2 calibrations, one for each mode. We also have a third calibration that's shown here. And I mentioned earlier, pardon me, about X offset and Y offset of the stylus tip. And this 4mm ball, 4mm diameter ball, is used to determine the relationship between this tip and the lower tip. And it does that in both the Y direction and the X direction, and that's used automatically for compensation by the PGI Novus. So this whole routine, the measurement on the top surface, lower surface, and the small ball calibration are all fully automatic. So form, radius, diameter, and angular accuracy benefit directly from the patented calibration routines and the combination of a low noise, stable platform, high gauge linearity, and also the traverse datum straightness. So all of these things go towards ensuring that we have good diameter measurements. One of the things to think about when we're measuring diameter is thermal expansion, and I'm going to deal just with the thermal expansion, the small thermal expansion of the part itself, of the sample that we're measuring. And in this case, we have a certificate for a ring gauge, where the ring gauge internal diameter is L. But then, having measured this in the laboratory and had it certified, measured at a certain temperature Tc, We then move it into the measurement environment, into the inspection room or the shop floor, where we look where we can see the effect of a different temperature. So we have the original diameter plus the effect due to thermal expansion, delta L. So in practical terms, we had a ring gauge of 40.00140 millimeters. We calibrated this and have a certificate for it measured at 20 degrees centigrade. The coefficient of thermal expansion for this particular item is 11.5. And the measurement condition, we went to the inspection room and measured at 21 degrees centigrade. That's a change of 1 degree higher. And we can see that this value here, this delta L value, this change in expansion is, in this case, 0.46 of a micron, just under half a micron. And so the corrected value is 40.00186. So we've gone from 40.00140 up to 40.00186. And at the levels we're capable of measuring at, we need to be very certain about temperatures. And this applies in the next example. So what we're measuring here is a 45 millimeter calibrated ring gauge. And we're recalibrating and setting up every 10 measurements. So we're calibrating, taking 10 measurements, calibrating, taking 10 measurements, calibrating, taking 10 measurements. The line in the center here is the 45 millimeter diameter, but we've actually compensated for the temperature as the temperature changes during these many measurements. You can see here in red, following that, the tolerance bands associated with the ring gauge calibration, ring gauge measurement, sorry. And in blue, finally here, we can see the results we actually got for that diameter measurement. And again, these have been compensated for temperature as well. So we've dealt with the slight changes in temperature over a very long period of time. And you can see that we're within 0.2 or 0.3 microns of the result of the original calibrated value. And the same again here, but this time we're calibrating, and then for many hours we're just measuring, measurement 1, 2, 3, 4, 5, and so on. And again, in green here, we can see the 55 millimeter calibrated ring gauge that we've used. Again, compensated for temperature, and the tolerance bands following that, the upper and lower tolerance bands, and then our measurements. And these measurements, again, within 0.2, 0.3 microns of the specified calibrated ring gauge known diameter. So truly excellent results here from the PGI NOVUS. So in summary, we've looked at a roller bearing application for diameter. We've looked at a ball screw application. We've considered the importance of alignment, and we've measured the pitch circle diameter. We've taken a look at the effect of stylus tip radius and form on the measurement of Gothic arch parts, such as a ball screw. We've looked at a very small diameter threaded bore application, and again looked at the pitch circle diameter and considered how important alignment is. We've had a look at the accuracy and repeatability checks made on a known 1 millimeter calibrated ball. We've seen how we can use long styli for diameter and roughness. and we can maintain the stylus force even on long styli. We've looked at the importance of cresting and gauge alignment, and we've had a look at the various methods using the column move or the direct gauge movement without moving the column, the different methods of measuring diameter while still maintaining very, very high accuracy. And finally, we've looked at the calibrations available. We've looked at thermal expansion and taken account of it, and we've looked at the accuracy and repeatability of diameter measurement. So that brings me to the end of the webinar, and I'd just like to thank everybody for listening. Please head to our website if you have further information that you would like to find, and that's at www.taylorhobson.com. And I'm happy now to take any questions. Thank you very much again. Just looking to see what questions we've got. One question we've got: can you tell us about diameter and radius measurement on Taliron systems? Yes, the original intent was to put the Taliron section in with this as well, but we found there's rather a lot of material, so we will be running another webinar dedicated to diameter and radius measurement on Taliron systems. So please look out for that on our website. I don't think there's any other questions today, and at that point I'm going to say thank you again and goodbye.